common misconception among students is that math somehow gets harder or has different rules once you get to algebra. But I would argue that the same exact rules that we used back in second grade for adding multi-digit numbers like this are the very same rules that we're going to go ahead and use as we add and subtract in algebra. Adding and subtracting in algebra is called combining like terms. Feeling doubtful? Let's see if I can prove it to you with the help of my student Channing.
Okay, so Channing, a lot of people get really mixed up when we start combining like terms, adding and subtracting in algebra. But I would argue that we're doing the same math we always did. So look at this problem I have over here. We probably would have tackled this in maybe like second grade, right? Channing, basic addition. Now, when your second grade teacher taught you to do a problem like this, we didn't go across, did we? She taught you to line up your work up and down, correct? So let's just talk about our strategy that we would use here if we were doing that, because the lining up matters. So let's think about this. If you were adding this number, 235, and this number, 61, I could line it up on the left. I could line it up on the right, or I could line it up, some random way. I don't know. Numbers are numbers, right? Can't I just line it up like this? I mean, why not? But there's only one way you'd work this problem. There's only one wise way to go. Channing, which way would you go if you were trying to add 235 and 61 by hand?
The second one.
Now, I love doing this with my GED students. I really, really do, because it just shows me how little they understood in elementary school, because students get so caught up in how, and they very rarely know why. My question to you is not which one of these is right. My question to you is, why would it be wise to line my numbers up like this? I mean, what's wrong with this? What's wrong with that? Why do I prefer the middle way? Any thoughts?
Because everything is in the place value.
Everything is in the place value. Wonderful. So we go to line this up. I have the 5s and 1s lined up. That's what I'm about to add together, right? I'm about to add together 5 and 1. But this isn't just the number 5. This has a value based on its place. This is 5 what, Channing?
5 in the ones place.
Beautiful. Those are 5 1s, like having 5 $1 bills. And then go ahead and look at the 1 beneath it. That's 1 what?
That's in the ones place.
Good. So it's 1 1, which sounds confusing, but that's like having one $1 bill. Beautiful. So if I add 5 1s and 1 1, I get what?
It's 6 1s.
Beautiful. I get 6 1s. And the way we write that is we just put a 6 in the ones place of our number. Gorgeous. Let's look at the next column, Channing. Now, I know when you guys add it, you don't think like this. You just go 3 plus 6 is 9, but we're not really adding 3 and 6 here. We aren't. Sorry. That's the shortcut way you're thinking of it, but that's not what this is. That's not just 3, is it, Channing? That's 3 of something. 3 what?
Tens. That's the tens place.
Beautiful. And that's 6 of something. 6 what?
And 6 is the tens place too.
Good. Those are both tens. So when I add 3 10s and 6 10s, I get
9 10s.
Good. Now, we're so lazy, we don't write 9 10s. We just write a 9 in the tens place. That's what we're saying when we put that 9 there in the tens place, that we have 9 10s. Now, how about the next column? What would I do there?
And then that's the hundreds place.
It sure is. And in my answer, what would I end up with in the hundreds place?
We just have 2.
Yeah, we have these 2 hundreds over here, and we have no other hundreds to put together with the hundreds. We just have the 2 hundreds. Now, I mean, I suppose you could say we have no hundreds here. It's 2 plus 0, but we don't have to. We instinctively know if there's only 2 hundreds, there's only 2 hundreds. So now we see here that what does this number represent? It represents that we have 6 1s, 9 10s, and 2 hundreds. Now, I mean, I suppose I could write this number out this way. I have 2 hundreds, and I have 9 10s, and I have 6 1s. but I don't have to in my number system because I have this wonderful place value system that lets me put those things together. 2 hundreds, 9 tens, and 6 ones. Beautiful. Then let's compare that to algebra. And I'd like to try to show you that even though we write about it a little differently, it's the exact same thing. Okay, so I'm going to make a problem that looks a lot like this one, except instead of hundreds and tens in our place value, I'm going to use variables. Instead of adding hundreds and tens, we're going to add x's and y's. Let's think of this number, 235. Instead of thinking of it like 2 hundreds and 3 tens and 5 ones, let's think of it like would probably happen in algebra. Instead of seeing 2 hundreds, we might see 2 x's. And you can translate and as the plus sign. Instead of seeing 3 tens, you might see 3 y's.
In algebra, do you always say and? Like,
no, you don't have to, but what I'm trying to show you is that adding is the same as saying and.
okay.
So I don't write the plus signs. Remember we talked about over here, the 200 plus 90 plus 6?
Yes.
I don't write the plus signs when I'm writing the number 296 because this is a shorter, easier way to do it because of place value. We have a place value system, so we don't have to write it like this. But I don't have that with my x's and my y's. There's no place value. I know if it's an x or a y based on where it is in the number. And so I only have the option of writing this out with the plus signs. So I have 2x and I have 3y. Now we said this is 5 ones. You know, a 1 is just a plain old number. It's just 5. And so I'm going to write that this way too. So I have just 5. So 2 x's plus 3 y's plus 5. And I'm going to add that with like my second number here, 61. So I'm going to make this 6 here be y's. So I have 6 y's in that number 61. And then this 1 is just a plain old 1 and a plain old 1. So I will write it as a constant term. So this problem over here that looks so scary, algebra, combining like terms, oh my God, what am I going to do? Is going to work just like our other problem. The only difference is I don't go up, down. In algebra, I read across and then put the answers underneath. So that's going to feel a little weird to us. But still, as we go to combine, we're going to see the exact same thing happening. So let's look at our first term here in here. My first term is 2x. Channing, go scanning through this expression here. Do you see any other x terms?
No, I don't.
No. Me neither. And so in algebra, when you are adding and subtracting, you can only add and subtract like terms, the same kinds of things. So there's nothing to combine 2x with, so I just have 2x. Now let's look at our next term and circle it with your sign, positive or plus 3y. Do you see any like terms? Any other y terms?
Yes, 3y and 6y.
Good. Now keep it with its sign. So positive or plus 3y and positive or plus 6y. Okay, now you could do the math in your calculator. And I know a lot of students are like, I don't have to, Kate, 3 plus 6. But man, when we're thinking this hard about algebra, don't feel one bit bad about adding 3 and 6 in your calculator, okay? What is 3 plus 6 or positive 3 plus 6?
Positive 9y.
Now I'm going to do something really interesting here. I'm going to put plus 9y. So I have 2 x's. Let's read that as we think about it. And 9 y's. Beautiful. Now let's look at our next term.
So plus 5 and plus 1, the symbol's the same.
It's not that the symbol's the same. It's that they're both plain old numbers. You know, they're just one thing. It's just 5. It's not some 5 of some mystery number X or 5 of some mystery number Y. It's just a regular old plain 5. Do you remember what we call that in the land of algebra?
Constant numbers.
Constant. So constants can always, always, always combine with constants. Okay. It's not about positive or negative. It's about the fact that they're both plain old numbers.
Okay. That helps.
Does that make sense? Cool.
Yes.
So what would I get if I combined positive 5 and positive 1?
Positive 6.
Beautiful. So let's read this answer. This answer says I have 2 x's and 9 y's and 6. And we've said a lot. We can't go any further than this. But look back and look at our answer from our arithmetic. Look what it says we have. We can read this using our place value system. It says we have 2 hundreds and 9 tens and 6 ones. And we could literally even write it out like this. Now you really wouldn't, because you're so lazy. I'm so lazy. We're mathematicians. I don't know what kind of English majors you think we are. But we could say we have 2 hundreds and 9 tens and 6 what? Well, 6 ones, just 6. Looks a whole lot like this. 2 x's and 9 y's and 6. We're doing the same math we always have. Nothing has changed since 2nd grade. There's not new rules in algebra. It's the same dang rules. Now we write it in a little differently. You're learning a new language, but you are not learning new rules.
It reminds me of It's a Small World, because it's all connected, everything.
Oh, well, that's the longer I teach math, the more I realize that, Channing. I'll be like, oh, this is just like that. Oh, this is just like that. You know, we think there's all these separate rules. When it's like this, do this. When it's like this, do this. When it's like this, do this. And part of that is how they taught us in elementary school. It's not really our fault. That's how they taught us. And I say, no, bull, just bull, 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 bull. There's one rule of addition and subtraction. There's always been one rule of addition and subtraction. It doesn't change. It's never changed. You can only add and subtract the same kinds of things. Period. Forever and ever. Amen. I don't care if you're talking about whole numbers like we just did, or if you're talking about decimals. My students say, Miss, you have to line it up at the decimal. I'm going to show you an example. 21.6. They tell me, if I want to add that, I gotta line it up at the decimal plus, I don't know, 5.45. And I say, how come you line it up at the decimal? How come? How come? How come? Screw these rules that are like, if it's a decimal, do this. If it's a whole number, do that. If it's a variable, do this. Channing, why am I lining it up at the decimal?
Because of the place value.
Amen. So I can keep the place value in line. It's not about the damn decimal. I'm sorry, I get so excited. It's about the place value. I wish your elementary school teachers would have taught you that. Not line it up at the decimal, but line up the place values, so that we're adding ones with ones and tenths with tenths, hundreds with hundreds, and hundredths with hundredths. Now, everybody's least favorite subject in the world, fractions. Like, I can make grown men cry with fractions. But sometimes adding fractions is easy, and sometimes adding fractions is really not easy at all. And what makes the difference? Why is one of these an easy problem and one of these I have to remember a lot of steps? Do you know which one of these problems do you know how to do? Do you know how to do either of them, Channing?
The first one, you add the top and then keep the number on the bottom the same.
Exactly. But how come? Let's go ahead and read this problem up here. Now, a lot of students will say this has 2 over 5, and that's true. There's nothing wrong with reading it that way. But right now, I'd like to read it the other way. 2 fifths. Read that problem for me then.
2 fifths plus 1 fifth.
Good. I have some number of fifths, whatever the crap those are. And then I have some number of fifths, whatever the crap those are. So if I add 2 things and 1 more of the same kind of thing, I have 3 of those things. I have 3, in this case, fifths. Now, this problem on the right is a hard problem. This is the one that makes the grown men cry and run out of the room because there's so much work to do. What makes this problem more challenging than the last problem, Channing?
The numbers are all mixed.
Yeah, I don't have the same kinds of things this time. This time I have 1/3 and 2 sevenths. I cannot put together thirds and sevenths. And so I have some work to do. Now, it's nice if you learn about fractions, you'll learn how to give them a common denominator, how to turn them into the same kinds of things. In the world of fractions, we can do that. And so that's all the steps you memorize and all the things you do and all that stuff your 4th grade teacher tried to teach you and you started crying and then you decided you hated math. But the point being, why is this hard? Because they're not currently the same kinds of things. And if I want them to put them together, I have to turn them into the same kinds of things. And this is not where this stops. And I could go on and on all day. And probably you guys have already stopped this video because you're so flippin' bored because Kate says the same things again and again and again. And I get it. But the point here being, this is how it's always been. It's that way in word problems. I add apples and apples and oranges and oranges. You know, I don't add seat and people and then say I have seat peoples in a word problem. You just don't. And it even extends up to algebra, right? I add X's and X's and Y's and Y's. And guess what? You're going to come up on even harder math where the same exact rule applies. It's going to apply forever and ever. Amen. I'm going to give you a great example that might scare the holy bejeebubs out of you. I mean, it just might scare you so bad, but I just want to show you what's coming. You don't need to know this for the GED, okay? It's not on the GED, but you're going to see it in your college classes, and there's going to be all these students who cry and scream and don't know what to do. And it's those who do not see the pattern here. So again, I'm going to write two expressions, and Channing, you've never even seen expressions like this in your life, but I bet you'll be able to tell me which one's easy and which one's hard. Okay, I'm going to read these two for you. Okay, the first one says 3 square root of 7 plus 7 square root of 4. And the next one says 3 square root of 5 plus 7 square root of 5. One of these is an easy problem that anyone can do. And one of them would take calculator work, decimal work, rounding. It would be nasty. Any thoughts? Which one do you think might be a simpler problem?
The second one.
The second one. How come, Channing? How come?
Because you have the same constant numbers in the square root.
Yeah, it's not necessarily constant number that you're not sure what language to use since this is all new to you. But yeah, we have the same number in the square root. In this case, we're counting up some number of square root 5s. Whatever the crap square root 5 is, I have 3 of him. And I have some other number of square root 5s. And so using this same exact rule that you've been using since 2nd grade, we can apply this to really challenging math. If I have 3 of something and 7 of something, and I put them together, I'm going to have how many?
So 10.
10. Wonderful. And 10 what? What kind of thing were we counting? I had 3 square roots of 5, and I put them together with 7 square roots of 5. So I have 10 what?
The square root.
Of 5. Just like 3 apples plus 7 apples is 10 apples. 3 square roots of 5 plus 7 square roots of 5 is going to be 10 square roots of 5. Confusing. Something you've never seen before. And yet we had a chance to accomplish it if we know one rule forever and ever, amen, throughout math. And that is, we can only add and subtract the same kinds of things. That's all you need to know. Stop trying to memorize if this, then this, if this, then this, if this, then this, if this, then this. That's all you need. If adding and subtracting gather up the same kinds of things.
Are you adding the 5 and the 5 together?
No, because it's just like with fractions. Come back to this one. Did you add up the 5 and the 5?
No.
No. How come? Because that 5 wasn't telling you how many. That 5 was telling you what kind. This was 2/5. And this is 1/5. I'm telling you how many of what kind.
Okay.
And this is new to you. And like I said, this is not on the GED. You don't have to know how to do this, but it's the same idea. I'm telling you, I have 3 of this thing and then 7 more of this thing. And so in total, I have 10 of this thing. And we're going to see it work that way again throughout math. When I added 10s and 10s, I had numbers in the 10s place. When I added apples and apples, I had apples. When I added X's and X's, I had X's. And guess what? If I'm adding square roots of 5s and square roots of 5s, I have square roots of 5s. Beautiful, beautiful, beautiful. Adding and subtracting is adding and subtracting. I don't care what you're adding and subtracting. Thank you, Channing. A great job. Proud of you. We did hard work.
I don't want to leave without saying a super big thank you to my patrons. on Patreon who support me every single month. You guys are the ones who enable me to do what I do, and the ones who are making sure that GED students across the world have access to the resources that they need. So thank you to every one of you. And I can't forget to thank those of you who have donated on Buy Me a Coffee as well. Whether you've become members like Valerie, Buffa, Andrea, and Brent, thank you, or you've done a one-off donation of a cup of coffee or 2 or 10. I so appreciate you. Thank you all so much for your support.